Students, today inshallah we'll be starting lecture number 3 series about transformers, and we will be solving few of the examples related to transformers. And the first example that we will be solving is from the book, the textbook by P.C. Sen. And here, let's see what's the question. Say that tests are performed on a single phase 10 kVA transformer. We can see it is a step down transformer. The primary side is actually the high voltage side, and the secondary side is the low voltage side, and the following results are obtained. So here actually it is the tests are given in a slightly confusing way related to how it is covered in the theoretical aspects. First of all, it says that the open circuit test was conducted by high voltage side open. So for example, if we have a transformer and it's a physical transformer, and what we were doing were we were performing open circuit test. So the high voltage side was opened, and the voltages, currents and power were calculated at the lower voltage side. So all the relevant voltages were applied and the things were calculated at the low voltage side. So the voltage, for example, the voltage source was applied here, and the voltage was 220 volts and the current was 2.5 amperes, and it was 100 watt was the power. So by using these parameters, we know that by open circuit test we are able to calculate the parameters of the core, the magnetization branch. So by using these parameters, what we will calculate will be actually the parameters. We will calculate these parameters, but they will be the parameters being reflected on the secondary side, the low voltage side. So it will be these parameters are similar to the parameters when we have parameters reflected to the secondary side, and when we have parameters reflected to the secondary side or the low voltage side, in this case, this is how it looks. Okay, so if these are towards the low voltage side, and if you want to convert them to the higher voltage side, in this case higher voltage side is the primary side, so we have to multiply them with a square. Similarly, these two parameters were calculated for the open circuit test, and they will be the values that we will calculate will be the values reflected at the lower voltage side, because these values were measured at the low voltage side or the secondary side of the transformer. Now for the short circuit test, look, it is low voltage side was short circuited and these values were measured at high voltage side. So the confusing aspect that is not that confusing if you concentrate a little bit, they were calculated at these sides, these values. So short circuit test is used to calculate the value of R equivalent. So these values are calculated, these values are equivalent, and Z equivalent is calculated by the short circuit test. So whatever values we will calculate, they will be actually reflected towards the high voltage side, to the high voltage side, that is the primary of the transformer. What I mean, it is similar to the voltage, this an IP and this is AVS, this is IVS. So actually we have values calculated at two different sides of the transformer, and when we have to convert this, now this is reflected to primary, which is the high voltage side. Now if we want to reflect them to the secondary, we have to divide them by A square. So this is just initial understanding there to understand the confusing aspect of this numerical. Rest is very same and simple that we will follow, and I will again explain this when I will be doing the results. So the part A says that we have to derive the parameter of the approximate equivalent refer to the low voltage side. In this case, low voltage side is the secondary, and to the high voltage side, that is the primary voltage. We can represent this with HV and we can represent this with LV. This will be simpler. Other things that should be noted that is important, that we can see that V high voltage or H side rated is 2200 volts, and VL rated, that is given voltage, is 220 volts, and the power for the transformer S high voltage is equals to S low voltage, that is equals to 10 kVA. So we can calculate our values. So IH, the value of IH will be 10k divided by 2200. This is 4.55 amperes. This is the rated current at the high rate side, and for the low side we can say the rated current will be same power divided by 220 volts. So the low voltage side, in our case which is the secondary winding, will be having rated current of 45.5 ampere. So this is a general understanding of our transformer, which has an input to the output of 10 kVA, and these are the maximum voltage and rated currents at our high voltage and low voltage side of the transformer. Now let's look at part A. And in the part A, we have to calculate the approximate equivalent circuit referred to the low voltage side and to the high voltage side. So as I was explaining previously, let's try and make two circuits here. And this is because the short circuit and open circuit tests are performed at two different sides of the transformer. And here we have, so these are the two different sides of the transformers, and when we will refer, as I have told you, the transformer refer to the high voltage side, that is the primary side. We have VP, or we call it VH. Let's call it VH and IH, and here we will be multiplying it with AVL, that is actually AVS, and this is actually VP, primary and secondary, and this will be IL divided by A, which is actually IS divided by A, and these will be the impedances reflected at this side. And for the second model, if you look at the second model, for this model what we will be having is the reflected towards the secondary. So this will be VPA, or we can write VH over A, and we can write here AIP, that is actually AIH, and this is secondary voltage, that is actually what I am calling low voltage, and this will be secondary current, and this will be the secondary current, that is actually, yes, because it is reflected at this side. So these are the two equivalent models. This is reflected to high voltage side, that is primary, and this is reflected to low voltage side, which is secondary. Now for if we look at our circuit, the question, open circuit test is with the high voltage side open and the low voltage side. So the open circuit test will give me parameters when our system is reflected towards the lower voltage side. So these parameters, when I will calculate by open circuit test, I will get these values, and then I have to reflect them to this circuit. For the short circuit test, I will calculate these two values. Why? Because a short circuit low voltage side was opened and it was reflected to high voltage side. So high voltage model values will be calculated, and then I have to refer them to this. Only this is one aspect. If you can understand this, rest is very simple. So this was the aspect that I have explained second time. So let's calculate now the parameters which we can calculate from the open circuit test. So they have given us the power. This is the open circuit test. Here we have POC equals to 220 volts, IOC equals to, and VOC equals to 2.5 and 100 watts. So as I've mentioned, there are two methods through which we can calculate this. Let's look at the first method that is similar to what was practiced in the lab. So we are actually calculating this. We know this was open circuit, so no current was flowing here. All the power and the voltage here was the voltage VOC, and the current was flowing into the magnetizing branch, and the power was this branch. So this is RC and this is XM. So the first thing we can calculate is by the formula. We know that power being absorbed by RC is VOC square over RC, and this will become RC equals to VOC square over open circuit voltage, and this becomes around 484 ohms. And if you want to calculate okay, now to calculate IC, the current that is flowing through this, the current that is IOC is dividing into IC and IM. So I can calculate these currents by IC, and that will become IC equals to voltage across the resistor divided by the value of resistor that I have calculated. So I can calculate 0.45 amperes. This was RC, 0.45 ampere, and now I can calculate, because I know this is the inductive branch, this is the real branch. So the IOC current is actually is composed of two parts, real part and imaginary part, and by that formula I can easily calculate this thing. Magnetization branch current, that is IM, this branch current is actually equals to under root IOC square minus IC square, and this will then become 2.46 amperes and when we have this current 2.46 amperes, so we know the current IM that is flowing into this branch. We know we have calculated IM. We know the voltage across this branch, this is VOC. So we can calculate XM, VOC over IM, and this will become 89.4 ohms. So from this value I have calculated 89.4 ohms. Now initially I have shown you that there are the transformers can be referred to two sides. So what parameters have I calculated? What are the parameters that I have calculated now? From which side parameters are there? These parameters belong to the value of RC and IM. Just think for a second. Here is also RC RC and XM. Here is also RC XM. Here is also RC XM. But this will be the values of RC and XM reflected towards the secondary or the low voltage side, because these measurements were taken at the low voltage side. High voltage side was open. So I can call this RCL or XML so that it will be easy for you to remember. I have calculated these two voltages. Now the second, okay, so the other way to calculate the same values, there is another method also that you might have studied, and that method is related to calculating the admittance, calculating the theta first, that is equals to cos inverse POC over VOC IOC. And once you have the theta, you can calculate the admittance IOC over VOC and minus of theta. And by using this method, you will get the value of Y, and through Y, you can calculate the values. So for example, here we have all the values given, and we put these values here, and for the theta we will get 79.52, and the admittance value will then be, we have IOC that is 2.5 ampere, VOC 220 volts, and we perform this, we will get 0.0113 angle minus 79.52. We expand this. This is 2.5 into 10 raised to power minus 3 minus J 11.11 into raised to power 10 raised to power minus 3. If we take 1 over this value, that is actually RC, 1 over 2.5 into 10 raised to power minus 3, that becomes approximately 486 ohms. That is almost same. This is because rounding of error. And for the next value, if I take RCs here, for this will be the value of XM, 1 over 1.11 into raised to 10 minus 3, and XM becomes 90 ohms. That is also equivalent to 89.4 ohms or 90 ohms. So these are the two methods by which we can calculate these open circuit parameters. But whatever the method we use, we have calculated the parameters that are being reflected towards the secondary or the low voltage side. Why? Because these parameters were calculated at the low voltage side or the secondary side. Now we have to calculate the parameters that are R equivalent and X equivalent. They are again given at the two sides. Now let's see what test they have measured the parameters on the high voltage side, that is primary side. So the values that are given to us for the short circuit test, they will be used to calculate these parameters that are reflected on the high voltage primary side. And let's look at what are the values given. V short circuit is 150 volts, and I short circuit is 4.55 amperes. Let's make it. The V short circuit is 150 volts and I short circuit is 4.55 ampere and P short circuit is 215 watts. So now what we are calculating? We are calculating for our transformer. We are assuming that the magnetization branch is no longer here, and these are the two components, R equivalent, and this is X equivalent, and this gives us Z equivalent. So this is the voltage and this is the current that is flowing through that. So Z equivalent can easily be calculated by the Ohm's law, and the Ohm's law states that we know the power that is being lost here is P short circuit P short circuit equals to I short circuit square into R equivalent is reflected across the resistance. So if we put all the values, we have the value of I short circuit, we have the value of P short circuit, so the value will become 10.4 ohms. And remember, this is the R equivalent reflected at the higher voltage side. And now to calculate the value of X equivalent, first we know that we can calculate the value of Z equivalent. Z equivalent at high is, we see our I short circuit, this is 32.97 ohms. And now we have Z equivalent, we have R equivalent, we can calculate, because we know Z is equals to, this is actually equals to R plus XM, so XM will be Z equivalent square minus R equivalent square, and this will be under root. So if I put the values, we will get the value of XM equals to, XM again reflected to high voltage side, 31.3 ohms. This is the one method. The similar, we have used the second method. We can calculate theta, that is PSC over VSC ISC, and you can calculate the value. Theta will be equals to 0.31 and this will be 71.639, and we can calculate Z then. VSC ISC angle is theta, and VSC we know, ISC we also know, and theta we have calculated 71.639. So this will become 39.97 angle 71.63. So from here, if we expand this, the real part will be 10.5 ohms and the imaginary part will be 31.3 ohms. Again we get the same values, as this is same as this is same as this. So now these are the two values. Again, these are the two circuits. Of what side have we calculated the values? These are the values that are represented by the high voltage or reflected towards the high voltage of primary side. Why? because short circuit test was low voltage side was shorted and these values were measured at the high voltage side. So here we have now calculated these two values. We have calculated this value and this value. So let's what was the question we have? So we have to make the approximate equivalent circuits. So let's do it. Let's write the values for the approximate. So we have calculated open circuit parameters. Open circuit parameters gave us open circuit test for high voltage side was open, so it was reflected towards the lower voltage side. So the values of RC is 484 ohms and this is 89.4 ohms. Similarly, for this test, short circuit test, it was reflected on the primary side of the high voltage winding, and here it is 10.4 ohms and this is 31.3 ohms. Now, as you might remember very well that sorry, I have written incorrectly. These were the short circuit parameters were 10.4 ohms and 31.3 ohms here. Yes. Now we have to fill the other blanks, and we know that when we have to reflect towards the primary side, what we do is we multiply it by a square, right? So if we want to convert this parameter which is missing here, we have to multiply by a square, and for this parameter also we have to multiply by a square, so it will be reflected towards the primary side. Similarly, so let's look, if we then RC will become, this RC will be actually RC is equals to a square into RC, this is at high voltage, so I squares into RCL low, and this will become multiplied by a square 48.4 kilo ohms, because so A, if you have not calculated A, we have A is equals to 2200 divided by 220, that is 10. Similarly, this will be 89.4 multiplied by a square, and this will give us the value of 8940 ohms. So here your equivalent circuit is now complete for the transformer which is reflected towards the primary or the high voltage side. Similarly, now the equivalent circuit which is reflected to the low voltage or the secondary of the transformer, you will remember what we used to do. We used to divide. If we have to reflect towards the secondary, we have to divide by a square. So what will happen here? It will be similarly this value will be divided by a square, and this will become 0.104 ohms, and this value will be divided by a square, and it will become 0.313 ohms. So by this we have solved A. Now let's look at express the excitation current as a percentage of the rated current. So the excitation current is here. The excitation current we have is 2.5 ampere. Let's try to solve the part B. high excitation is 2.5 ampere, and this was actually measured at the low voltage side. In this case, this is the secondary side. So for the secondary side, we have also noted down this is the rated current. Dividing the total power by the maximum voltage, it is 45.5 ampere. So I rated at the LV side is 45.5 ampere. So the question it is asking is excitation current as a percentage of the rated current. So how we can calculate is 2.5 divided by 45.5 into, so how much was it percentage? This becomes 5.5%. So this says that the excitation current is only 5% of the full rated current compared, as I have recently told you also, it is a lower value. So the last part is determine the power factor for the no load and short circuit tests. That you have almost already calculated the power factors for the no load test. Look, this is, but let's see if you have already calculated here also, when if you were using this method, theta is equals to this, and cos of theta of this value is actually the power factor for open circuit test, and here you calculated theta, and cos of this theta is actually power factor for the short circuit test. But if you want to write it again, you can do it. So for the part C, you can do it like this. Power factor for open circuit test, this will be cos of theta equals to POC, VOC, IOC. They have given you these values, and this will become 0.182, and it is of course always lagging. And power factor for short circuit test will be cos theta power short circuit over V short circuit, I short circuit, and this becomes 0.315. The short circuit condition is 0.315. This is also almost always lagging. So in this way we have solved this question, and it has taken more time because I have solved it in two ways. But apart from the confusing element, rest is simple. Okay, best of luck.